Welcome back. In this video, we're going to talk about integration using trigonometric substitutions. So we are expanding on our methods or strategies for integrating difficult expressions. And what you see here, we have three triangles. And I'm circling now three pieces. I've got the square root of a constant squared plus a variable squared, the square root of a constant squared minus a variable squared, or a variable squared minus a constant squared. Okay, so when we have those three forms somewhere in a problem, this is a situation where we might choose to use trigonometric substitutions. And the three common substitutions, I'm going to draw a square around here in green, are either x equals that constant a times tangent theta, or x equals the constant a times sine theta, and x equals the constant a times secant theta. And that's determined by the form that we are given. Okay, so using a trig substitution is useful when you have any of these three items in the orange circles that I'm pointing to. And then the trig substitutions that we generally use are x equals a tangent theta, x equals a sine theta, and x equals a secant theta, again, depending on the form we have. We only have one for plus, but we have two for minus, and that's because subtraction is not commutative, right? You have to switch the whole thing around. So depends on the order when you're subtracting, but addition order doesn't matter, so we don't have to have a fourth where we reverse those. That would mean exactly the same thing. And you'll notice we have these bottom equations here. And I'm going to derive for you how we get a times secant theta. I'm not going to do all three because the other two would follow by a very similar argument. So let's say that we start with tangent theta equals x over a. If I identify it or organize it in that manner, and I draw a reference triangle with my reference angle theta in the lower left corner of this right triangle. And if tangent theta is identified as x over a, tangent's opposite x over adjacent a. And by the Pythagorean theorem, I can derive that this hypotenuse would be a squared plus x squared. So let's look at this. If I take that tangent theta equals x over a, I can rearrange it and say, well, x equals a tangent theta. So suppose I start with my radicand here, a squared plus x squared. Well, I can manipulate that and say, well, this is a squared plus x is a tangent theta, quantity squared. Distributing that square, I would have a squared plus a squared times tangent squared theta. Factoring a GCF, I have a squared times 1 plus tangent squared theta. And we all know by the Pythagorean identity that 1 plus tangent squared theta is equal to secant squared theta. So if I were to apply a square root on the left of this equation, I could apply a square root on the right. And square rooting that, I end up with a times the absolute value of secant theta. And I have to use those absolute value bars is because secant theta could give me a negative output. And if it's under the square root, it needs to be giving me a positive output. So here I have derived that last line that was on that first page. And a similar argument, you could create a triangle, put theta here. If you were dealing with sine theta equals x over a, then you would draw that triangle. Remember, sine is opposite over hypotenuse. x over a, then by the Pythagorean theorem, this side would be called a squared minus x squared. And you could complete a similar argument to derive a times cosine theta for sine. All right? And then if we were dealing with secant, if this is theta and I had secant theta equals x over a. Remember, secant is reciprocal to cosine. Cosine is adjacent over hypotenuse, so this would be hypotenuse x over adjacent a, which gives me, by the Pythagorean theorem, that this vertical side on the right would be x squared minus a squared. And then again, you could develop an argument similar to this, that x squared minus a squared could be called a tangent theta. Okay, so when we are dealing with these trig substitution problems, we want to determine the situation we have and then know the constraints that match up with each of these three situations. Now, of course, we want any substitution that we use in this integration, we want it to be reversible so that we can always change back to our original variable afterwards. And what I mean for that, by example, is if we had x equal to a tangent theta. Well, I might need to isolate that theta and say, well, theta is going to equal to tangent inverse of x over a. So I would need to use that inverse function, okay? And hopefully you all remember from your trig classes that these inverse functions, in order to make them functions, we create restrictions on the domain and the range. So I'm going to pull a picture in here. So what we know is that depending on the substitution for x that we use, we might end up with that inverse function. And if you remember those graphs, each of those inverse functions has a restricted range. And we need to make sure that that we specify that theta falls within those restricted ranges. And I know that the inverse range for secant looks pretty tricky, and that's because we have an asymptote on our inverse secant graph. But for our purposes in this class, we'll just use the top piece. Okay, we won't make it as complex as using both of these. So to summarize our strategy for using these trig substitutions to simplify integration of something that's complex, I've got these steps here for us. The first thing we want to do is write down that substitution for x. We want to calculate our differential, whatever dx will be, and then specify selected values of theta for the substitution. Then, depending on which of our which one of our three situations we have, we're going to substitute the trig expression and the calculated differential into the integrand. Then we're going to use algebra to simplify. At that point, once we've simplified, we can integrate our trig integral. Remember, you have to keep in mind the restrictions of the range of that inverse function so that we have angle reversibility. And then, draw an appropriate reference triangle to reverse the substitution on the integration results. Convert it back to your original variable x. All right, so we're going to start with something in x. We may switch it into a and theta. We want to be able to go back to that x. So this is kind of the intro to why we're going to be using those three formulas. And then in the following videos, I'm going to do some trig substitution integration examples.